I'm tackling a dimensionality reduction problem. I have a dataset with 1,000 data points, each having 10,000 features. My goal is to reduce the number of features while keeping the distances between data points similar. I'll use a technique called Johnson-Linden-Strauss lemma. I'm allowed at most 0.1 distortion. The question asks for the minimum number of features needed after reduction. This is the core question. What's the smallest number of features I can have while still maintaining the relationship between my data points? Allowing a maximum of 0.1 distortion, epsilon equals 0.1. I'm using a formula to estimate the minimum number of dimensions. N represents the number of data points, 1,000 in this case, and epsilon represents the acceptable distortion, 0.1. The formula calculates an upper bound. The formula, in words, is 4 times the logarithm of the number of data points, divided by the square of the distortion. I'm using a function called Johnson_Lindenstrauss_min_dim from a Python library called scikit-learn. This function helps me find an upper bound for the minimum number of dimensions needed. It doesn't give the exact minimum, just a value that's guaranteed to be high enough to satisfy my needs. I'm working with a large dataset containing 1,000 data points. Each data point is described by 10,000 features. That's a lot of information to deal with. Dimensionality reduction aims to simplify this. The Johnson-Linden-Strauss lemma is a mathematical result that tells me that I can reduce the dimensionality of my data while approximately preserving the distances between the data points. This lemma forms the basis of the dimensionality reduction technique I'm using. I see this option as too low. My calculations show a much higher upper bound for the minimum dimensions needed. The Johnson-Linden-Strauss lemma, which underlies the calculation, suggests a significantly larger number. This option doesn't align with the theoretical minimum. This answer is incorrect. Remember, we're aiming to reduce dimensionality, not keep it the same as the original 1,000 data points. The goal is to find a smaller number of dimensions to represent the data. This is still considerably lower than my calculated upper bound. While closer than option A, it's still too far off to be considered correct. The difference highlights that the calculation provides an upper bound, not a precise minimum. This is the correct interpretation. That's right. The Johnson-Lindenstrauss-mindim function in scikit-learn gives us an upper limit on the minimum dimensions needed. It doesn't tell us the absolute smallest number, just a number that's guaranteed to work. The large difference between my calculated upper bound and the given options supports this. I'll substitute the values of n, number of data points, which is 1,000, and epsilon, acceptable distortion level, which is 0.1, into the formula. 4 log n epsilon squared. This gives me an approximate upper bound on the minimum number of dimensions needed. The calculation is 4 log 1,000, 0.1 0.1, which is roughly 2,763. Remember, this is just an upper bound. The actual minimum could be lower. I've calculated an upper bound of approximately 2,763 dimensions. Looking at the multiple choice options, none of them are close to this number. This tells me something important. The Johnson-Linden-Strauss lemma's function only provides an upper limit, not the exact minimum number of dimensions. Therefore, the correct answer is D. The function gives an upper bound, not a precise minimum. I'm tackling a dimensionality reduction problem. I need to find the smallest number of dimensions I can reduce my data to while still keeping the distances between data points relatively unchanged. This is a crucial step in many machine learning tasks. I have a dataset with 1,000 data points. Each data point is described by 10,000 features. That's a lot of information. My goal is to make the data easier to handle without losing too much information. I'll use 2 key parameters. N equals 1,000, the number of data points, and epsilon equals 0.1, the allowed distortion or error in the distances between points after dimensionality reduction. The smaller epsilon, the more accurate the result, but also the more dimensions I will need. I'm leveraging the Johnson-Linden-Strauss lemma, a powerful mathematical tool that guarantees I can reduce the dimensionality while approximately preserving distances between data points. It guides my choice of the minimum number of dimensions. I'm trying to determine the minimum number of dimensions that satisfies the Johnson-Lindenstrauss lemma's guarantee, given my parameters. This is where I use the Johnson_Lindenstrauss_min_dim function or its underlying formula. The function I'm using gives me an upper bound, not the exact minimum number of dimensions. It essentially says, if you use this many dimensions or more, you're guaranteed to have an acceptable level of distortion. Finding the absolute minimum is computationally much harder. I get an upper bound for simplicity, knowing it's good enough for the task at hand. This option suggests keeping the original number of dimensions. That defeats the purpose of dimensionality reduction. I want fewer dimensions, not the same number. This is a possible estimate, but I need a more rigorous approach, backed by the math of the Johnson-Lindenstrauss lemma, to validate. This option is too low. It would likely lead to an unacceptable level of distortion in the distances between my data points. I'm tackling a dimensionality reduction problem. Imagine you have 1,000 data points, each described by 10,000 features. My goal is to shrink this data while keeping the distances between points similar. I'll use a tool called Johnson_Lindenstrauss_min_dim with a distortion limit, epsilon, of 0.1, meaning I allow a maximum 10% error in distance calculations. This answer suggests that I only need around 184 dimensions. That seems too low given the initial 10,000. This option proposes about 590 dimensions. While better than 184, it is still quite small compared to what my calculations suggest. This is the correct answer. The Johnson_Lindenstrauss_min_dim function doesn't find the absolute smallest number of dimensions. Instead, it gives me a guaranteed upper limit. I'm certain that the dimensionality can be reduced to that number or less, but the function cannot promise it's the very smallest. This is the core question. I'm looking for the smallest number of dimensions I can use while staying within my acceptable distortion of 0.1. Option B suggests 1,000 dimensions. That's the original number of data points, not the reduced number of features I want. Dimensionality reduction aims to reduce, not maintain the original number of features. This clarifies the goal. I need to decrease the number of features, and the acceptable error is 10%. Epsilon equals 0.1. I start with a dataset containing 1,000 data points, each having 10,000 features. It's a high-dimensional dataset, making it computationally expensive to process and analyze. This is why I want to reduce the dimensionality. I'm tackling a dimensionality reduction problem. I have a dataset with 1,000 data points, each having 10,000 features. My goal is to reduce the number of features while keeping the distances between data points similar, allowing for at most a 10% distortion. I need to figure out the minimum number of dimensions I need to achieve my goal using the Johnson-Lindenstrauss lemma and scikit-learn's Johnson_Lindenstrauss_min_dim function. This is a possible answer choice for the minimum number of dimensions. This is a possible answer choice for the minimum number of dimensions. This is a possible answer choice for the minimum number of dimensions. This is a possible answer choice, suggesting the function only gives me a maximum limit, not the precise minimum. I'll be using the Johnson-Lindenstrauss lemma, a mathematical concept that helps with dimensionality reduction while approximately preserving distances. Scikit-learn's Johnson_Lindenstrauss_min_dim function is a tool I'll use to estimate the minimum number of dimensions needed. Epsilon represents the acceptable level of distortion. In this case, it's set to 0.1, meaning I allow a maximum of 10% distortion in the distances between data points after the dimensionality reduction. N represents the number of data points in my dataset, which is 1,000. I'll use an approximate formula, 4 times the logarithm of the number of data points, divided by epsilon squared. This gives me an upper bound, which means the actual minimum dimension could be lower, but will not exceed this value. My dataset has 1,000 data points, and each data point is described by 10,000 features. That's a lot of features. This is why I want to reduce the dimensionality. My aim is to reduce the number of features, dimensions, to a smaller number, while making sure that the distances between data points are only changed by a maximum of 10%, epsilon equals 0.1. This is crucial to maintain the integrity of the data.